Hi everyone, I just want to quickly go through a couple of things that you had asked me to go through just in the lead up to the SAC that might make things a little bit easier for you, hopefully, particularly if you missed a couple of sessions early on, maybe you missed some head start or something like that, or you're a bit unsure. Hopefully this helps. So starting with significant figures, which is essentially rounding, but when we deal with rounding, generally speaking, you'll have like a 2.2 round to the nearest decimal place. Okay, so that's 2, right? This works in a similar way, but instead of rounding after a decimal place like you normally would, you actually round the whole figure itself, right? It's a way of rounding an entire figure, and there are a couple of rules, so I'm going to go through them just to make sure you understand them. So rule 1, probably the most important rule: anything that isn't a 0 is considered to be a significant figure, or a Sigfig, we call it for short. Right, so the number 28, for example, has 2 digits, 2 and 8, neither of them are 0, therefore it has 2 significant figures. Right? Rule number 2 is zeros that go between significant figures are also significant. So 808, even though there's a 0 in the middle, because it's between 2 significant figures on their own, it means that there are 3 in total there because it's in the middle. Right? Leading zeros are not significant, right? So in this case, I've got 0.003201. These first 3 zeros are not significant. Then I find a non-zero, which is, this one is a non-zero, which is, and this is a 0 separating significant figures, so it is, and then lastly the 1 is also significant, meaning it has 4 significant figures. So those 3 rules are the main ones, and they're probably the easiest to understand. The last 2 are a little bit trickier, so just so they make sense. Trailing zeros are significant if they're after a whole number and there is a decimal place. So for example, 92.00 would be 4 significant figures, and the reason for that is essentially you've said that, for example, this was in kilometers. You would say it's 92.00 kilometers. That means that you've actually measured beyond kilometers down to like the 100-meter mark, right? And you'd say that this is exactly 92.00. Therefore, that measurement is important and worth noting. But if you don't want to think of it that way, just understand that if it's 0.0, 0.00, anything like that, those zeros are important, right? Next, trailing zeros with no decimal place are not significant. Alright, so 520, that 0 is not important because there's no decimal place. So there's 2 significant figures right now. If I put 0.0 in, there's 4. But because there's no decimal point, that 0 is not important. Okay? So just so you get the hang of it, if I was going to round 7,438.05 to 2 significant figures, what I do is just like I would after a decimal place, I count 2 values across, so 1, 2, right? And then the next number, I round up or down, right? Based on whether it is less than 5 or greater than 5, or sorry, greater than or 5. So 3 is less than 5, therefore I have to round down. So 2 significant figures for this number would be 7, 4, right, and now I'm rounding down, so 0.00, right? So I've rounded that down entirely, yeah, because it wants only 2 important figures, right? If I were to do that same number to 5 significant figures, again, I count across 1, 2, 3, 4, 5, right? The next number is 5, meaning I round up. Therefore, that would be 7,438.10, right? So it's worth noting that that rounding has happened. Now, one thing that's important to remember is that in this case here, I need to get rid of these 2 zeros on the end, right? I've just done that just to show you how this has worked. But this is technically right now, that isn't 2 significant figures, that's like 6 significant figures. So I'm just going to get rid of those 2 zeros so it makes more sense. And same with this one, I'm just going to get rid of this last 0 because otherwise it's going to think that it's more specific than what I'm going for, and that's not true. Alright, so they're my answers for those 2 significant figures. Now let me just scooch this up a smidge. If I were to round 0.00276 to one significant figure, remember that leading zeros are not important, so I'm going to skip them. I'm going to write in my, well, before I write in my 2, that's where I'm going to look at. The next number is 7, means I round up, so this should actually be a 3, not a 2. That's my fault for writing it in prematurely. Right, and there's zeros. Okay, so I've rounded up from that 7, which has made this a 3. Okay, let's try two significant figures. Same thing, 0.00. So 2 is my first significant figure. My second one is 7. My next number is 6, meaning I'll round up that 7 to 8. Right, so 0.0028. Right, tilt this up again. Okay, so then sometimes you might have a question like this, that how many significant figures are in this thing, right? How many are here? Well, I can go and count them. This is 2.00658. Now going back to my rules, all non-zeros are significant, meaning that I've got 1, 2, 3, 4, right? Also zeros that are in between significant figures are significant as well. So those are significant also, meaning I have 1, 2, 3, 4, 5, 6 significant figures. All right, how many are in this one? Remember, leading zeros are not significant according to rule number 3, which means I start counting from here. So that is a significant one, and that is, and this is between values, that is also, right? So that's 3 significant figures. And the only other example that I tend to throw out there is if you had something like 220.0, right, would be 4 significant figures because you got 1, 2, and normally a trailing 0 wouldn't matter, but because there is a decimal point, it means that we've measured beyond what we're looking at here, so these are considered to be significant. Right? I know that's a little bit tricky, but that's okay. Let's flick over. Let's talk about scientific notation, right? Because I had a couple of people ask me about that. If you're unsure about scientific notation, basically the process is that you want to write your number out to be in a form like this, where it should be one number, a decimal point, and then followed by a bunch of decimals, times 10 to the power of something. Okay, and the way that we figure that out is what we do is we find where the decimal place is in our whole number. So in this column here, our decimal point would have been there, right? And we move this back however many spaces we need so that it is, I guess, before the first digit. We go back 1, 2, 3, 4, 5, 6, meaning that's where that decimal point would be now. And now I can write this out. So I'm just going to write out the significant figures here that are not zeros. I'll just put it that way. I'm going to write out the non-zeros. So 2.675, right? That's what's important to write out because the zeros doesn't matter, times 10 to the power of, well, to the power of how many spaces did I move back? 1, 2, 3, 4, 5, 6. So times 10 to the power of 6. All right? So you can see how this sort of ties in. Because these are trailing zeros, they're not significant, so they're not worth writing down. So it sort of links into the significant figures thing that we were doing before. Let's look at this one here. So we've got 0.00681. Now this is a smaller number, so I'm actually going to go back in the other direction. But I want it to be in a point where it'll be a number, point, whatever. Right? Meaning this decimal point will have to move between this 6 and 8. That goes across 1, 2, 3 to go there. All right, so I would write 6.81 times 10, and remember I moved across 3 times, but because this is a smaller number, as in less than 0, I need to make this a negative, so it's a negative 3. So I move back negative 3 spots. All right. Yeah. Now you can actually go the other way too. All right. So this time we have the number given to us and we got to make the whole number, and it's just basically undoing that process. So I'm going to write out this 2.461 times 10 to the power of 3. Remember, it's a positive, so it's going to be making this number bigger. So I'm going to go across 1, 2, 3 spots. I'm just going to put it there, meaning my answer is 2,461. All right. So it wasn't a particularly useful example because it didn't simplify anything, but that's okay. And we'll try the same with this one. So again, we're going to do this 2.25 times 10 to the power of negative 5. So I'm making it smaller, meaning I'm going to be counting in the other direction. And I move it 1, 2, 3, 4, 5. My decimal point is going to be over here now. I might be like, well, what do I do in this situation? For all of these bumps, I'm going to have to write a 0 in. Alright, so 1, 2, 3, 4. Right, and because they're not significant zeros, it's not going to do a whole lot. It's not going to change the number or anything. But that's how I take this out of this scientific form. So I'm going to tidy this up a bit so it's easy to see. So it'll be 0 point, and I've got 4 zeros. So 1, 2, 3, 4, 2, 2, 5. Right, and that's my thing there. Right, that's my answer. The last thing we look at is order of magnitude, which is essentially how many times would you need to multiply something by to multiply by 10 to make it the number that it is, essentially. All right. So let's pretend if I want to find the order of magnitude of a single number, all that's asking me is essentially if this was written in scientific notation, what would the power be? All right, that's all it's asking. All right. So in this case, it would have been decimal point would have been here. So 1, 2, 3, 4, 5, 6, 7. So that would have been 1.0638 times 10 to the power of 7. Therefore, the order of magnitude is 7. All right. Similarly, you can have other questions that go a little bit like this, that if a ball weighs 2 kilos and a globe of a statue weighs 2,000 kilos, what's the difference in order of magnitude, right? So I'm looking at what's the difference between these two sizes. How many times bigger is this one compared to that one, right? So let's look at that as in we have the globe weighs 2,000 kilos, the ball weighs 2 kilos, right? Which means that it is 1,000 times bigger. Yeah, 1,000 times heavier. I can rewrite this 10,000 as 10 to the power of 3, because 10 to the power of 1 is just 10, 10 to the power of 2 is 100, 10 to the power of 3 is 1,000, meaning the order of magnitude in the difference between these two is 3. Right, and sometimes it won't work out as perfectly clean as that, and that's okay, but that gives you an idea of what we're looking for. Okay, hopefully this fills in some of the gaps. Yeah, have a great day. Good luck with the SAC.